Hello, good evening everyone. So this is week 4 discussion for the NPTEL course Solar Photovoltaics Fundamentals, Technology and Applications. And this course is being taken by Professor Soumitra from Department of Physics, IIT Roorkee. I am Ravi Kumar, a PMRF Research Scholar at IIT Bombay. I hope you have gone through the lectures of this week. Yes, no? You can just write in the chat box. Yes, okay. Okay, so in this week, there is only one concept that is DSSC, dye sensitized solar cells. Okay, we will look into it. What about others? They haven't? Okay. So questions are very easy from this course. Let's start. First, just let me know the examples of different generations of solar cell. I'll write here first generation, second generation, and third generation, because currently we are in third generation in the lecture series. Just write what do you know about first generation, second generation, third generation. Silicon belongs to crystalline silicon, or monocrystalline, multicrystalline belong to third, second, or first? Vinod said crystalline silicon. Okay. So first generation is crystalline silicon. Amorphous silicon, which category? Which generation? Second. Okay. So second generation we have amorphous. And DSSC, dye sensitized solar cell. So in general we can say these are the crystalline. These are thin film. We have cadmium telluride as well. So these are thin film. And in the third we have DSSC and organic peroxide, etc. So today we are going to study about this DSSC, and we will do some questions based on this dye sensitized solar cell. This is the generation of solar cell. So first generation we have silicon. In this silicon we have crystalline, that is single and poly. Mono, we also known as like monocrystalline and multicrystalline. Second we have amorphous, cadmium telluride and CIGS, that is copper indium gallium diselenide. So these are thin film technology. And then we have DSSC. So different material like GASH and old quantum dots as well. Sorry, peroxide is from fourth generation, and then we have hybrid. Hybrid we have tandem as well, and multi-junction, etc. So this is the topic for today's week. DSSC, dye sensitized solar cell. So what is this dye sensitized solar cell? First we need to understand it, then we need to look into the working of this solar cell. So this represents our dye sensitized solar cell. There are few components which you need to understand, like we have electrolyte, we have electrode, one electrode and second electrode. So these are the electrodes. These are nothing else, just glass having one side conductive material layer. So some layer is there that is conductive in nature. Similarly, for the counter electrode, we have glass and then it is conductive layer here. After that, what we need, it says die. So we need a die. So second part is die. It is a dye sensitized solar cell. Third component is this material, titanium dioxide. I'll tell you what is the working of all these components. And then the fourth one is electrolyte. So these are the important component of dye sensitized solar cell. Okay, so what happens when a light strike on the surface of DSSC solar cell? Let's see. When light is coming from a light source and it is striking on the surface of DSSC, so this dye will excite, and due to this excitation of dye, what will happen? There will be an electron generation, and this electron means this electron is generated by dye, and this electron will be captured by this titanium dioxide. Means through this titanium dioxide it will go to this outer electrode, and from this outer electrode it will go to load. So here we have load. So this is all about the electron. But on the other hand, what will happen? This dye is now at excited state. It is like excited state and it is ground state. So what is happening? Solar light or sunlight is striking on the surface of dye and it is being excited. Due to this excitation, generation of electrons is taking place. But now our dye is at excited state. So for continuous operation, because this is a one round of operation, so for continuous operation, this dye need to come down into the ground state. So that's for that reason we need an electrolyte. So this electrolyte will give electron and this dye will come to the ground state. And the electron given from this electrolyte will be gained back through this outer load circuit. So this electron will come back here. So this is the way this circuit will be completed. So this is dye sensitized solar cell. Here we don't need any PN junction. And this is very easy to make. Even you at your place can make this solar cell. Any doubt here?
No, sir.
Okay. So, okay. So let's watch a video about this DSSC fabrication. So this is around 10 to 12-minute video. We will see it. We will watch it together because I think many of you haven't done the lecture, so I might miss it.
Hi, I'm Hannah. I'm a junior at Pomona College. I'm a chemistry major, and today I'm going to be showing you a simple way to make solar cells that convert light energy into electrical current using very simple components such as blackberry juice.
Hi, I'm Connor Comerlo. I'm also a chemistry major at Pomona College. I'm here to work with Hannah on the solar cells because solar cells are awesome. To make them, we're going to need to use blackberry juice, microscope slide, titanium dioxide, and an iodine solution.
The type of microscope slide that we'll be using is coated on one side with a special conductive oxide. This will form one side of the solar cell. So the first thing we have to do is determine which side has the conductive oxide. To do this, one thing we can do is use a UV lamp. One side will fluoresce and one side will not. So we see that this side is fluorescing. That means it's the glass side, so we don't want to use that side. But see, this side doesn't fluoresce, so that's the conductive side, so we want to use the side that doesn't fluoresce. We can also use a multimeter to see which of the sides has a voltage across it. Your instructor can help you out with that version.
Our next stage is to tape the slide down to the table. When you tape your slide down, make sure that 3 of the sides are taped to about 1 millimeter on the edge, and that one of the sides is taped with about 3 millimeters of tape covering the edge. Also, make sure that all of the sides of tape are sealed onto the paper, sealed onto the slide.
Our next step is to make the titanium dioxide paste that will form the semiconductor for our solar cell. So here I've weighed out 1 gram of TiO2 powder. So now I'm going to take this and put it in a mortar and pestle. Now I'm going to add approximately 2 milliliters of ethanol. In this step, you can use ethanol, you can use propanol, you can use dilute nitric acid, but for this solar cell, we're going to use ethanol. Now I'm using a pipette to add it, but all you really need is just some way of adding it slowly. So you can also use a graduated cylinder. So here I'm adding 2 mils. And now I'm going to stir it with the mortar and pestle. You can add more solvent if you need it to get it into it should look like white paint or sunscreen at the end.
Now that we have our paste, it's time to add our paste to the solar cell. Your paste should have the consistency of watery shampoo. You can take a spatula and add 3 drops to the solar cell. Now you want to smooth out these drops across the solar cell with a glass rod. Maybe. That's up to you, Hannah.
Our next step will be to heat the TiO2 paste over an open flame. This will remove the solvent and allow the TiO2 to bind more strongly to the glass slide. So in our setup, we have a Bunsen burner underneath a ring stand with a wire mesh gauze on top. And be very careful when using an open flame, and always have a lab coat and safety goggles on. So now we'll remove the tape from the glass slide so that we can put it over the Bunsen burner. Note that because we had the slide taped down, our TiO2 now makes a nice neat square on top of the glass slide. Be sure to remove all the tape. Now we're going to put this on top of the mesh and light the Bunsen burner.
Heating the slide drives off the solvent that we added to the TiO2. Remember that this is a really hot system, and that cold glass looks exactly like hot glass, so do not touch it, you will get hurt. Also, with your flame, you want to have the inner tip of the flame just about touching the microscope slide, so that you have the hottest part of the flame touching it. A key component of a solar cell is a dye that can absorb light and turn it into energy. For our dye, we're going to use a dye in blackberries that we can crush up and put onto our solar cell. First, you crush up the blackberries. Once we've mixed the blackberries thoroughly, we want to add 95% ethanol right here. We want to add 12 mils of the 95% ethanol. We also want to add 12 mils of 15% acetic acid. Now you want to stir this up thoroughly too. Once you've stirred it up, you take a coffee filter, place the coffee filter over a beaker, and filter the dye.
So now we have our final filtered blackberry dye. We're aiming to get about 10 mils. That's plenty for what we are going to do. Now I'm going to pick up the TiO2 slide and simply submerge it in the blackberry juice. And it's going to sit there for 10 minutes. So while our semiconductor slide is soaking in blackberry juice, we're going to prepare the second slide that makes up our solar cell. So again, I've determined that the top side of the slide is the conductive side. And now we're going to coat a layer of graphite on top of it to help the electron flow. Our source of graphite is going to be a pencil lead. So I'm just going to put this down. And now I'm just going to color, basically, a layer of graphite on top of the slide. Don't be afraid to scrub hard on it. I'll draw on it again from another angle to make sure it's totally covered. And there's our second slide. Make sure that the entire square is coated thoroughly. So here you can see our graphite slide. So now we've got our two final microscope slides. Now we're going to assemble our solar cell. So here we have our slide that was removed from the blackberry juice it was in. And here we have our graphite slide. Now what we're going to do is put a couple drops of this iodine redox couple, which is going to serve as the filler for the dye. Once the dye molecule has lost an excited electron, the redox couple replenishes it so that the circuit is completed. Now I'm just going to take 2 drops of this and put them on the graphite slide. And now I'm going to lay one on top of the other, making sure that on each side a little bit of the glass is hanging off. This will allow us later to help test the slide. The final step is to seal the solar cell. To do that, we're going to use 2 binder clips. Now, I'm going to clip the clips on the 2 sides that aren't overhanging. So there's one clip, and here's the other one. And there's our solar cell.
So this is our final and complete solar cell. So now the only thing left to do is to go outside and measure the voltage it produces.
So now we're going to take our solar cell outside to test it. Here in sunny Southern California, we have plenty of sunshine. So what we're going to do is we have a voltmeter, and we're going to connect the 2 electrodes across the solar cell.
And it looks like we're getting about half of a millivolt of electricity. So that's good.
Great, so this concludes our demonstration of making a dye-sensitized solar cell, and good luck in building your own.
Thank you.
Okay, so you have seen the demonstration. So just let me know which material they use for the electrolyte and which material they use for the dye. So from the video you can see like it is very simple to make a DSSC solar cell, and they use blackberries to extract dye, and they use iodide redox couple for the electrolyte, and for this metal conductor they use graphite from the pencil. So it is very simple to make a DSSC solar cell. If it is so simple, then why this technology is not commercialized yet? It is, but it is not on a large scale. So there are 2 drawbacks. One is low efficiency. So they are having around 11% of efficiency. And second is solvent problem. Means we are using electrolyte that may leak from the solar cell or solar panel. Yes, we know, you are right, leakage issues. So this electrolyte may leakage because a solar cell should work in the field for about 20 to 25 years. So this electrolyte may leak in this large span of time. Okay, so this is all about DSSC. Now we will do some questions. So first question says, dye sensitized solar cell are invented by, and these are the options. And these were invented in 1991. Vinod said A. Okay. Michael, Gergel and Reagan. Yes, this is the right answer. So correct answer here is A. Next question is about the redox mediator in DSSC. So it says, which among the following is the example of redox mediator in the DSSC? Redox mediator means electrolyte, and these are the options. B. Everyone is saying B. Yes. Yes, Chandan, Vinod, Boris, Tafi. Yes. It is B. Iodine. Next question is about which pigment is responsible for absorption of light in plants. So it is related to photosynthesis, which you have studied in your 7th or 8th standard. So which pigment is responsible for absorption of light in plants? Chlorophyll, stroma or xylene? Chandan said A. Chlorophyll.
Chlorophyll.
Yes, due to this chlorophyll only, the color is green. And this is colorful. This is nothing like it. This is just a dye. So the main motto behind this DSSC is this photosynthesis process. Scientists thought this chlorophyll thing or this photosynthesis can be generated in the lab, and they invented this solar cell. Yes, A is the correct answer here. Next question says, what is the limitation of liquid electrolyte in DSSC? Limitation, I just told you. These are the options. What is the limitation of liquid electrolyte in DSSC? Disensitized solar cell. Vinod Kumar said solvent leakage. Yes, Yashu leakage. Chandan Kushwa leakage. Yes. Yes, it is solvent leakage. So correct answer here is solvent leakage. Next question is about the quantum dots. In zero dimension quantum dot, motion of electron is restricted from, and these are the options. D, all direction. Yes, Vinod. So do you know what is this quantum dot? Why the name is quantum? Okay, let me tell you. Whenever we go to nanoscale, the size decreases. Yes, it is nanoparticle, and quantum means very, very small. So what happened? Let's consider any material which is in the form of a cube or cuboid. So here a atom or an electron can move in any direction. So we said this is a 3D material. When we just restricted this motion in the one direction, from one direction we are restricting it, so it will move only in this side, up and down. So this is said as two dimension. and we just then restricted it from the two direction, then it will move only in one direction. This is the atom can move this way or this way. So this is 1D. But for the quantum thing, we are restricting a particle from all direction. So we just get an dot structure. So our atom will be restricted here, or our electron will be restricted here, and that is known as zero dimension. So this question was related to this only. In zero dimension quantum dot, motion of electron is restricted from all direction. And correct answer is D. Next question is a numerical, and I want you to solve it. Just take your time and solve it, because we don't have much questions regarding this week. So I just want you to solve this numerical. So it says, what is the short circuit current delivered by 10 centimeter by 10 centimeter DSSC photocell with 100% quantum efficiency? It is being illuminated by monochromatic light of 400 nanometer wavelength with a power density of 1000 watt per meter square, and these are the options. Please solve it. If you need any help, just write in the chat box or ask directly, I will tell you. It's very simple question. It is nothing like a rocket science, very simple one. Just need to like relate to different quantities, and there are no many like given values, only 3. I can tell you the one thing for the time being. It is saying 100% quantum efficiency. What does this quantum efficiency means? Let's say this is a solar cell and photon is coming like this. This is our photon. So what will happen? This photon will generate an electron. So 100% efficiency means number of photon will be equal to number of electrons. This means 100% quantum efficiency. Take your time, solve this question. Ask if you need any formula or anything else. Sir, formula please. Okay. I'll just tell you the concept. First, calculate the power incident on the surface of solar cell. Second step, calculate the energy of given wavelength. So here it will be energy equals to hc by lambda, and here it will be area into insolation. And then third step will be find out number of electrons or photons, that will be equal. And fourth step is find out sir, I go through lecture yet I am unable to. Chandan, this numerical is not in the lectures. Even there is no formula in the lecture related to this. I am telling you, this is very simple. I am writing here step. You just ask me which step is difficult for you. Find out total charge, and then fifth will be current will be charge upon time. So first step, just calculate the power incident on the surface of solar cell. If anyone have calculated the first step, they can just write the answer here. I'll write against the step number. Is it 10? Yes, it is 10. It is 10 watt. It is nothing like just 1000 into area of solar cell. And area is 10 centimeter into 10 centimeter. If you will calculate, it will come 10 watt. So this is the first step. Second step is very simple, Hc by lambda. You know this, right? 10 watt. Hc by lambda. H is given, C is given, lambda is given. Then what is the problem? This is H, this is C, and this is lambda. Four point 497 10 to minus 19. Others, please verify because I haven't calculated. There is no calculator. Others, please verify Hc by lambda. 4.9. Vinod, I am getting 4.9695. Just check it.
4.9 4.8 आता है सर.
4.9 na? Yes.
हाँ 4.9.
Yes, yes. So it is 4.9. I can write 7 into 10 is power minus 19, and unit will be in joule.
Joule per second. Sorry, joule second.
Joule second. Why joule second? Second will be gone na.
Yes. हाँ
HC
सर, sorry. Okay,
only
got it.
joule.
हाँ.
That is the energy na. Energy will be in joule only.
Joule.
Yes. Okay. So second step said 4.97 into 10 to the minus 19 joule. Now third step is number of electron or number of photon. See, this 10 volt, what is it? 10 joule per second. And we are having energy of 1 photon. So to make the energy of 10 joule in 1 second, how many electron or how many photon is needed? So just divide the required power divided by the power of electron. If you haven't understood it, let me know. I can repeat it again. Yes. See, wavelength is the wavelength of photon. So we have calculated the energy of 1 photon, that is hc by lambda, and this energy of 1 photon is 4.97 into 10 to the power minus 19 joule. It is clear? But the energy is incident on the surface of solar cell is 10 joule per second. Means in 1 second there is 10 joule, and 1 photon is giving only this much energy. So how, just consider the 1 second only. So in 1 second only, how much photon will be needed to generate this 10 joule? Let's say Y is the required energy and X is the energy of photon. So X is this and Y is 10 joule per second, or you can write in 1 second only 10 joule. So just divide 10 divided by this 4.97 into 10 to the minus 19. That will be the number of electron or hole. Yeshu saying 2. What is 2? It is answer B or 2.3. Or step 2. Vinod, you got it? $2.01. What is 2.01? You are dividing 10. Which step is 2.01? Just let me know what are you saying, right? This 2.01 is the answer of third, fourth, or fifth step. Number of electron. Only 2 electron will be there. Just think, if this is the energy of 1 photon or electron, to generate 10 joule, it is even minus 19 joule. So only 2 electron will be enough. Yes, even you have not written it like correct way. It should be 10 raised to the power 9, 19. Yes. Let me calculate for my simplicity. 10 divided by 4.97. Yes. 2.01 into 10 raised to the power 19 electron or photon. This is the answer for third step. So that much photon or electron will be generated. Now, if we know the number of electron, can we calculate the total charge? Yes. Then please do so. Charge of electron is 1.6 into 10 raised to the power 19 coulomb, and x into charge of electron, x into charge of electron means number of electron multiplied by charge of electron. 3.2 coulomb. Yes. So it will be 3.2 coulomb. And what we are doing? We are calculating in seconds, and we already considered second 1 second. So here T is already considered 1 second. So how much current it will be? 3.2 ampere. Yes. So answer here will be B. 3.2 ampere. 3.2 ampere. A, B. Okay. B is the right answer. Yes. Others, if you are having any kind of difficulty, just let me know. If you are having any difficulty in either step 1, 2, 3, 4, 5, and in any step, just let me know if you are having any difficulty in any step. Step 4, find total charge. Chandan, in step 3, you got step 3, you got total electron. See, Arinda 4, I am saying total charge need to calculate it. So total charge should be number of electron into charge of electron. Just need to multiply. And charge is already constant 1.6 10 to the power minus 19. And this number of electron was 2.01 into 10 to the power minus 19 plus 19. You just multiply them, it will come around 3.2. So 3.2 coulomb will be charge. And for the step 5, our current is total charge divided by time. Time we are already taken 1 second, so total charge 3.2 coulomb divided by 1 second, it will be 3.2 ampere. Very simple. Step 2, please. Okay, what is the step 2? Calculate the energy of given wavelength. Step 2. Our lambda is given 400 nanometer, and energy defined for an electron is Hc by lambda. H is given 6.8 6 to 6, I don't remember, into 10 to the minus 34 joule second into, this is H and this is C. C is the speed of light. It is 3 into 10 to the power 8 meter per second divided by 400 nanometer. Just this second will go and this nanometer just converted into meter, 10 to the minus 9 meter. So there is no nanometer anymore. And just calculate it, you will get the energy of single electron. What was that? Let me just see. It was 4.97 into 10 raised to the power minus 19 joule. So this will be the energy of single electron. See, just look at it. We have a solar cell and these are the photons. This is a single photon of having 400 nanometer wavelength, and this is 10 into 10 centimeter square size. Total energy coming on this surface can be calculated like this: 1000 watt per meter square into 0.1 meter into 0.1 meter. So it will be around 10 watt. So total energy incident on the surface of solar cell is 10 watt. Means in 1 second it is energy is equal to 10 joule. If we know the energy of one photon from this 400 nanometer, can't we calculate the total number of photon coming in 1 second? Yes, we can. So number of photon will be equals to 10 joule divided by E, that is calculated from Hc by lambda, and this was coming around 2.01 10 to the power 19. It is number, unitless, because both side is joule. We are calculating in the second. Now I said 100% quantum efficiency. So number of photon will be equal number of electrons. So this much will be number of electron as well. So total charge will be number of electrons into 1.6 into 10 to the power minus 19 coulomb, and we were getting it around 3.2 coulomb. And then for the current, just Q by T, and T was 1, so it was 3.2 ampere. So this is the physical understanding. We know the energy of one photon coming in 1 second. So how many photon need to be there to get this 10 watt or 10 joule energy in 1 second? And from there we calculated number of photons. From the quantum efficiency we got number of electron, and then from the total charge and from the charge per unit time we got this 3.2 ampere current. Any doubt here?
No, sir.
Okay. So 3.2 is the answer here. Next question, similar question, just give me the answer. If you are unable to solve, let me know. Same step will be followed. I'll tell you step by step if you have any difficulty. Question 7. It is saying the power density of monochromatic laser light is 5.86 nanometer. It is to be monitored, means it is incident on the surface of 1 mm into 1 mm DSSC solar cell. What current do you expect if the light level is 230 watt per meter square? Exactly same question. You just need to calculate current I, and these are the options. Take your time, solve it, and let me know. I will just write a step here. 1. Energy on the DSSC solar cell. How much? Second, energy of photon. How much? Third, assume 100% quantum efficiency here as well. Third, number of electron. Fourth, total charge. Fifth, current. If you are solving it and if you are getting answer of any step, let me know. I'll write here. P. Vinod, can you just give me like number with units and which step? Power is 230. It is given 230 watt per meter square. Vinod, are you asking about this power or are you telling me the answer? Step? No, sir. Doing, yes, yes, do it. Take your time. Energy of photon, step 2, right? Step 2, 10 raised to power 16, wrong. Or it is minus 16. Minus 16. Minus 16, then it can be 6.626. .39 is right, but 10 to the power 16 is wrong. Yes, Chandan, minus 19. So energy of photon here will be 3.392 into 10 raised to the power minus 19 joule. Number of electron 68 into 10 raised to the power 19. I need to check. Others, please do so. No. 68 and 12. No. We know it is not right. What about Chandan? Step 3. step 1, you know you are wrong in terms of this exponential or like power of. Yes, yes. So even exactly 6.78 into 10 raised to the power 14. Yes, you are right. Okay. Chandan, step 3. Step 3 is just to find out number of photons, means step 1 divided by step 2. This is step 3. Energy incident on the surface of solar cell divided by energy of single electron or photon. One charge, total charge. Sindhu, let me calculate. You have got 1.6 into 10 raised to the power 1.32 is wrong. 0.1088 Coulomb. We know it is not right. You are messing with this power of 10. And I am sure you are wrong in the step 1. One zero eight microampere, yes. Yes, we know. It is 108 microampere. Others, please solve it. See, energy on DSSC solar cell will be 230 into 10 raised to the power minus 6 watt. Step 1 will be this. For step 2, you just need Hc by lambda. For step 3, just step 1 divided by step 2. For step 4, just step 3 into charge of electron, that is 1.6 into 10 raised to the power minus 19 coulomb. And for the current, step 4 divided by time. Time is 1 second. Very simple. We have done step 1, 2, 3. For the step 4, any answer here? It should be 1.08 into 10 raised to the power minus 4 coulomb. And for this step 5, 1.08 into 10 raised to the power minus 4 coulomb divided by 1 second, it will be 108 into 10 raised to the power minus 6 ampere, which can be said 108 micro ampere. Any doubt here? If you still have any doubt, you can ask. So answer here is C, 108 micro amps. And with this question, as we have one more question, it said, which is not a method for quantum dot synthesis? And these are the options. If you have done the lectures, then you will be able to solve it. Yes, it is thermal deposition. Thermal deposition is not the step for the quantum dots. These other two are. So answer will be C. So we are done for today. We will meet next week. I hope you understood the concept. Also, you are able to solve some questions and you have learned something new. Okay, welcome everyone. So if you need to ask anything, you can ask. Otherwise, you are free to leave.
Thank you, sir.
Yes.
Thank you, sir.
Okay. You are welcome, Chandan. Chandan, you are saying, sir, one doubt. If you have any doubt, you can ask. In exam, there is only MCQ or any other type. How can we get the answers of assignment? Sindhu, assignments are supposed to be solved by you. I am taking the assignments from the previous year, and the answer which are coming for this year, they need to solve by you, and answers will be reflected after the due date. So after the due date, if you will see the assignments, you can see the answers as well. Yes, I can. Definitely I will. And like Chandan said, each exam there is only MCQ or other type. See, I am not from this exam setting department and all, but I I can say it will be an MCQ only. This question you can ask on the discussion forum. They will be able to give you more clarity on this. Maria step, yes, DSSC mechanism I can show you once again. First I'll tell you four important component. We have a glass with some conductive deposition. We have another glass with other conductive deposition. In between we have a die. This is electrode. This is counter electrode. This is die. And we can make some so in the die what we have some energy levels. In between there is an electrolyte. This is electrolyte. And here we have titanium dioxide material. So what happens as the light comes on the surface of this solar cell, the atoms here having an electron hole pair and they got excited. They go to the excited state and they remove an electron here. This electron moves from this die through this titanium dioxide to this glass. So this is the path of electron. And from this glass it is being collected by the electrode and it go to the outer circuit. And this is our load. What happens? This die is in excited state here. It is excited state, it is ground state. So this is only one cycle. But we need to reuse this die again and again. So what we will do? We need to bring this die from excited state to ground state again, so that this can be reused again and again. So for this purpose, this electrolyte will give electron to this die. And after getting an electron, this die will come from excited state to ground state. Sorry, that is not visible here. So here we can see it will come to this down. It will come down. This electrolyte is giving electron to this die and it is coming down. So this is a complete path. Light strike on the surface of die. It will give an electron. It will be collected through this titanium dioxide, and it will go to the outer node. And this excited state will come to the ground state by using this electrolyte. And this electrolyte is sort of an electron, and this electron will be given through this circuit completion. And this is a redox couple, means redox reaction will happen there. It will lose an electron and it will get an electron. So this is a cycle here. There is no P injection in DSSC. I hope you got it. Okay. You are welcome. Next time we will see some other technology. Okay, take care. Bye bye. I am ending this class.